methods, contemporary methods, and so I think that's one of IBM's roles, to help with elevating the level of the students and perhaps the faculty in their ability to leverage big data methods. Okay, it's coming in and out of volume, but hopefully it's bearable. Okay, with that, this is a little bit of the outline of what I'm going to be talking about. First, I'm going to describe what's meant by big data. Then we'll go into some of the classical problems that arise once you have big data. And I'll then transition to describe some of the methods that are employed at a high level. We're not going to go into great detail, but I'm going to give you some of the classical methods first. And I'm going to break down these classical methods into 3 classes, so-called supervised, unsupervised, and semi-supervised machine learning. And then I'm going to touch upon, perhaps in too great length, and I may breeze through some of these slides, some of the more advanced, latest methods in machine learning. Then, my final 2 topics, I'm going to explore some of the ways in which we're starting to use data and a little bit of big data in meaningful ways in the water sector. And finally, well, actually, not finally, there's one more after this point, some potential applications in the water sector. And lastly, I'll describe the IBM Research Africa internship opportunity that have been mentioned. So we will have up to 1 student intern sitting with us for each of the TORs. Okay, hopefully 1. But if I'll show you what we're looking for in these internships. If we don't get any, we won't have any. Okay, so first of all, I should give Clara some nice credit for making my very unaesthetic slides much more aesthetic. Thank you, Clara. Yeah. Okay, so excuse the fact that I have to use these glasses for reading. Okay, so what is big data? So it's a term that describes that large volumes of data, both structured and unstructured, inundates businesses and organizations on a day-to-day basis. But it's really not the amount of data that's important. It's what we do with the data that's key. And the idea, in businesses anyway, and I think also in the public sector, is to use this data for better decisions, on the one hand. And a theme that is often underemphasized, but important in the private sector especially, is to use the trends that are emerging from this data to proactively motivate new business directions. Okay, so there are 4 V's, so-called V's of big data. And this is a concept that came into the mainstream in the 2000s. An industry analyst, Doug Laney, he introduced 3 V's. Nowadays, people talk about the 4th one, and I think the 4th one is actually one of the more interesting and problematic, that of veracity. So the first one is volume. So obviously, we're getting increased amount of data. With the advent of the internet, of course, people are creating data. We have more images, video, but also you have a lot of data now that's coming in through machine-to-machine communication, sensors in the world that are producing data, and we're trying to make sense out of all that volume. And with volume comes the increased velocity of data. So the more we instrument the world, the faster the faster the data comes at us, and it exceeds our ability to store the data. So we have to judiciously make a snap decision. Is this data interesting enough for me to store, to analyze further? And that's often not an easy problem. Then the variety of data. So data is coming at us in both structured form, traditional numeric data that we store in databases, but also increasingly in unstructured, what's called unstructured format. So that's text documents, images, and video. So data that has to be processed to some extent for it to be utilized. Numeric data we can analyze right off the bat. But images, text data, we have to do some pre-processing for the data to be useful. And then the last one, which is especially interesting in the modern world, is the veracity of the data. So we get a lot of data, but some of it is not accurate. Sometimes it's noisy. Sensor data comes out noisy. It's things that we think are factual turn out not to be factual. And there's an important adage in this business that garbage in, garbage out. Right? So you have to, especially I think in the groundwater field. We've been doing some work as IBM in the north of Kenya, and we have all this data about all the boreholes that are up there. But it's an amazing collection of junk. I mean, so you really have to go back and clean the data before you can make great conclusions or draw conclusions from this kind of data. Here's a sort of infographic I got. It's an IBM infographic that talks about these big four. I'm going to actually skip this, but the slide is interesting. And so I suggest that if you're interested in the topic, to go back to the data that's posted for everyone, or the slides that are posted for everyone, and explore some of the implications of these four V's. Okay, so what are some of the classic problems that arise from the fact that we do have big data? So one of the most common problems that people in this field solve is that of categorization. So given data, say about a new patient, does the patient that comes to worried about having cancer, do they have cancer or not? And if they do have cancer, what's the grade of the tumor? It's classic categorization issues. And a funny one, more funny, but one that comes up a lot is there a particular object in an image? For example, you see an image, can a machine automatically detect if there's a dog in the image? Okay, then a problem that we probably all learned about in school is that of regression. So given some input variables, predict the value of an output variable. The output variable can be a single scalar or it can be a vector. And so an example problem of this sort is, given the myriad of atmospheric variables, what is the likelihood that it will rain tomorrow? So given all the data that we have today about the atmosphere, can we say if it's going to rain tomorrow in Joburg? Then clustering. So given a collection of data points, can we cluster similar data into clusters? Next, summarization. So given some text, say a news article, can we automatically produce a summarization? And just this week I heard about an exciting project that IBM is doing. So about the Wimbledon tennis tournament. So a task for the organizers or the press coverage of Wimbledon, they take footage of all the great tennis matches, the interviews with the players, all these things, and at the end of the day, they have to quickly put together a summary reel for the news outlets. IBM has just won a contract to do this automatically, and the results are actually quite impressive. So a simple thing to do is, if you have a some video footage of a tennis match, and all of a sudden the crowd is going wild, that's a good indicator that this might be an important segment for the summary reel. Also, if the announcer is getting all worked up, it's probably a good indication that it should be footage for the summary reel. But a key issue is, how do you bound that segment so that it's meaningful for the viewers at night, or retrospectively. Okay, then the next one is, given time series data, so isolate the important trends, or including anomalies. So for example, given some sensors that are, so flow sensors, say, on some water infrastructure, when is failure of the piping, or of a well imminent? Then the last area that I'll mention, although there are actually some additional ones, something that you're probably all familiar with, although perhaps not by this name, is the notion of collaborative filtering, or recommender systems. So based on your purchase history or anything else about you, can the system recommend an additional item that you might be interested in? Okay, so now machine learning problems of this sort are typically categorized into three different buckets. So the most common one is what we call supervised learning. So we get a set of data points together with labels, and we have to reproduce labels on new examples, which aren't so labeled. So for example, given a history of rainy or not rainy days, which are the labels, which we can get from sensors, and the preceding atmospheric data, determine whether we're going to have a rainy day given some new atmospheric data as we go forward. Then there's unsupervised learning. So the classic problem in unsupervised learning is clustering, grouping common things together, but you don't have an a priori notion of what the similarity means. And another type of unsupervised learning is isolating trends. Sometimes this actually can be thought of as semi-supervised or supervised learning, but let me not go into that nuance. So just isolating trends in data also is or anomalies is a unsupervised learning issue. Finally, there's semi-supervised learning. So this is actually very similar to supervised learning, except for the fact that it's, in this case, ordinarily expensive to label the data. So you can't get, all the data doesn't come to you pre-labeled. So an example is, suppose you're trying to determine whether there's a dog in an image. There's lots and lots of images on the internet of dogs and no dogs. People, you have to pay people or get somebody to spend their time to label whether there's a dog in the image or not to get the ground truth. But it's ridiculous to expect that every single image on the internet would be done by a person like that. So this is an example. You have a limited number of labeled data. You have to make inferences on new unseen cases on whether there's a dog or not. Okay, so first I'm going to go into some of the classical methods of machine learning. Hello? Okay, some of the classical methods of machine learning, and then we're going to look at some of the more state-of-the-art methods. So first of all, there's regression methods. There's linear, what are called linear and logistic regression. So you probably all learned about linear regression in school at some point. So this is where we assume or hope that there's a linear relationship between the input variables and the output variables. So you may have 1, 2, 3 variables, and you hope that there's a linear relationship among them. So a relation of the form y equals ax1 plus bx2 plus cx3 plus d. Okay, if you spent much time on this problem in school, you think it's a very important way to approach a problem. But it turns out not that many relationships in real life have linear dependence on the input variables. And a more common form of regression used in machine learning is what's called logistic regression. So here, the output variable isn't unconstrained in its possible values, but is constrained to sit between 0 and 1. And we model it with what's called the logistic function, a complicated function which you may not have seen before, but trust me that this function 1 over 1 plus e to the minus x, it ranges in value from 0 to 1. So for very large values of the input variable, large negative or small negative values, i.e. values going to negative infinity, the value of the logistic function goes to negative infinity, and goes to 0, and as the input variable goes to infinity, the output variable goes to 1. And just like you can feed a linear combination of input variables to in linear regression, you can replace the input variable z with a linear combination of variables here. And this turns out to be a much more useful method of regression in most machine learning tasks. Okay, so for example, if I was to decide whether there's a dog or not a dog in an image, this may be a linear combination of features, or say I have a cat. I like cats better. So if I see that there's a tail in the image, that's somewhat indicative of a cat, or ears, somewhat indicative of a cat. But to distinguish a cat from a dog, I also probably need whiskers or something else, right? But I can't combine these features linearly to determine whether it's a cat or not. But I can do that in a certain sense using the logistic function and logistic regression. And here you might think of a number very close to 1 being indicative of my confidence in there being a cat in the image. And so some linear combination of these 3 features where you have different weighting based on your experience seeing, I don't remember what the 3 variables were. One was whiskers, one was eyes, ears. Okay, I think those are the 3. So based on experience, I would learn what an appropriate weighting for those 3 input variables were. But the output would scale from 0 to 1 based on my confidence that there was catness, or a cat in the image. Okay, another type of classical machine learning method is a decision tree. Okay, you've probably seen this tongue-in-cheek decision tree. But the key is not to come up with something like this by hand, but rather to learn the decision tree from data. Okay, so that's the second key method. I'm not going to go into great detail. I think each of these classical methods are wonderful. And if you're so inclined, if you've never seen these things before, I encourage you to look at the literature to learn more. Just whetting your appetite on each of these methods. A third important method of machine learning it applies to binary classification problems. In other words, the cat or no cat problem. But here, I have some explanatory variables which I put on the axes. Here I'm saying there are two numeric variables, and they're on the x and y axes. And I'm trying to separate the black points from the white points. Here you can see it's very easy to create a line separator, a linear separator. And the purpose of the idea of this support vector machine notion is in a very high number of dimensions, we want a linear separator. And in a high number of dimensions, we call the separator a hyperplane. And the idea is to find what's called a maximum margin hyperplane. So while a hyperplane here does separate the points, the maximum margin hyperplane is the one that sort of goes optimally between them. Okay, so for linearly separable points, this is not a hard problem, but this method has actually been modified to work relatively well for certain kinds of nonlinear problems, using what's called the kernel trick. And so we transform this problem, which has some curvilinear structure, into one which doesn't, using the so-called kernel trick. Okay, another method of contemporary importance is what's called Bayesian methods. And Bayesian methods appeal to an important rule known as Bayes' rule. So it says that if you have two events, A and B, that the probability of A given B is equal to this. Actually, you know something? I think that going into great detail, this method is going to be too much. So I'm going to glaze over this a bit. And the key purpose of Bayesian methods is we have some prior understanding of the likelihood of something. So here we have a prior understanding of what the parameters of a model might be. We're going to update this prior knowledge of what the parameters of a model should be based on the data that we receive. And that's the whole idea of this Bayesian machine learning. So we take a prior knowledge of something, say it's the prior knowledge that, so in the prior example. Okay, so in this example, we have patients that come into our clinic with liver disease. And we have a prior about the probability that people who have liver disease come in as alcoholics. We all know that if you're an alcoholic, you have a much higher probability of having liver disease than a patient in the normal population. And as we see more and more patients, the idea is to update this model. And of course, there's many, many other parameters that indicate whether a patient has liver disease. And so a true Bayesian model is not just based on this one variable of being an alcoholic, but it could be many other things. You could have taken certain, medication concentrates in the liver. Well, many medications do. So if you have a history of taking certain kinds of medication, you're also going to be more inclined to have liver disease. And so as you update your assumptions about all the parameters of this model, these Bayesian methods give you a principled way of updating such a model. Okay, now just a little taste of what some more advanced methods of machine learning are like. Okay, so it comes somehow going in and out, is it me moving must be me moving the microphone back and forth. Okay, so a problem that we run into often in machine learning is what's called overtraining a model. So let's look at this example. And so this method in particular, a method called random forests, tries to overcome this problem. So suppose I have a set of data, as indicated here. So there's X is the input variable, Y is the variable we're trying to predict. And you can see that a line fits this data pretty well. But if we want to exactly hit all the data points, we could fit all this point data with a high degree polynomial. You can see that this high degree polynomial goes through every single point. But suppose we get a new data point, say right here between -4 and -6, say it's -4.5. Do you think we'd be better off using the line or the high degree polynomial? Okay, probably not the high degree polynomial. It'll predict the value all the way up here. Okay, so by picking this high degree polynomial and hitting all the points exactly, we're overfitting the data. And so we're better off with a line here. And there are other ways to overfit data. So if you have here, we're trying to separate the X's from the O's. Well, a line is not such a great fit here, but a simple parabola, second degree curve, does a pretty good job. I could create some crazy curve that completely separates the X's from the O's. But do you think that's going to be very good at predicting new values? Probably not. So it's an example of overfitting. Okay. Okay, so the idea actually is, Clara did a little not so great job on this particular slide in her aesthetics. So, but in any event, the idea of random forests is not to use one very complicated tree, which tends to overfit in many examples, but rather use very small, random, use a lot of small random trees. So it's a kind of bad example that I came up with was, suppose I want to go on vacation, and I want to come up with a good tree to help me make my decision, but I don't have access to train the tree on me. I just have access to my friends. So I can go around to all my friends, and I can come up with some very bifurcating tree that will completely help or make a good decision for each of my friends. Will this tree necessarily make a good decision for me? Perhaps not. So another approach is to just ask a couple of questions in a very short tree and ask me many of these two-level questions. So for example, one of the small trees might be, where did you go on vacation last? And did you like that place? That gives a lot of information. So if you ask many, many small trees, they have the potential of actually providing more information while at the same time avoiding the overfitting problem. So one of the most important methods of contemporary advanced methods in machine learning is deep neural networks. Okay, it's based on the observation that much of machine learning is based on one simple problem, that of estimating a function, an unknown function, giving a good, simple estimate. So you have a function, you want to basically give it a whole bunch of points that you know the function value of, and a new point produce a value for that function. So here's two examples. One very simple, one much more complicated. So suppose we have an image. So the input for an image is a set of pixels. Right? We're not a human being. We can't see it as one single input. We're a computer program. And we get say a 640 by 480, one of the old-fashioned small images, and we have RGB in each pixel. And from that, we have to output either a 1 or a 0, depending on whether I see a dog or not a dog. Okay? Another much more sophisticated problem, but a problem I like, is given a position in chess, find the best move. Okay, so you may know that nowadays we have computer programs that can beat the best human chess player, actually by a wide margin, and much, much better. And so here, what we do is given a position that's described, a chessboard is an 8x8 matrix. So you have a 8x8 matrix of integers describing the locations of the pieces, and what we want to output is the probability of winning from that position. So how does that give us a good program? Well, we're given a position, we provide the position, we generate all the legal moves, and then based on what legal move gets us to a position with the highest probability of winning, we pick that move. Right? So that's why even chess, so two problems seemingly as dissimilar as finding a dog in an image and finding a best move in chess, they both can be solved if we have a good function approximation. Okay. Okay, so taking a bit too long. So for some practitioners, including myself, we use traditional shallow neural networks for a long time. And this was a curious topic of research, but it really didn't make that much traction. So it had success only in a couple of domains, principally in game playing. The first big success in backgammon, beat the best human backgammon player. And then in a famous IBM example, we used it in Jeopardy game strategy. And also somewhat famously in task and motion planning, especially for robots, where there's a very precise goal. Okay, but until recently, it was considered impractical to consider deeper networks. So the machines weren't fast enough, not easy enough to get access to multiple machines or cluster of machines to do the workload needed to create a deeper machine, to exercise a deeper machine. And also we didn't have algorithms. Even though we knew this was a way to represent more sophisticated functions, especially for problems like detecting dogs in images or understanding what's going on in a video, because we didn't know how to leverage the machine power, we didn't spend a lot of time developing the algorithms to approximate these more sophisticated functions. Okay, so this first slide, I'm actually not going to go into great detail. I think I've already told you that linear regression really doesn't model too many practical problems, especially too many classification problems. And so we don't use it very much in contemporary machine learning. Instead, we use logistic regression, which I've gone through this already. And it turns out that logistic regression is one of its, actually there are many ways to do logistic regression. You don't have to use the logistic function. But in any event, this is the function that we typically use to model a single neuron in deep neural networks. So the idea of a neural network, it's modeled after a brain, what we think goes on in the brain. And a single neuron takes a whole bunch of outputs, and these outputs are translated into a single output. These inputs are translated into a single output. And we give weights to these inputs. And the way in which we model the activity of a single neuron is using the logistic function, or a relative of the logistic function. And the output of one neuron in a deep network feeds the input of successive neurons. Okay, so this is what the deep network looks like. The input is coming in from the bottom, the output from the top. And the idea of the input, these are in the classification problem of dog or no dog, these are the pixels, the pixel values. Or in a chess game, these are the values of where the pieces are, or no pieces are in the representation of the position. The output is what we have to determine. So in the case of it can be a single output. So either it's 1 for a cat, 0 for no cat, or the probability of winning for a position. But it can also be vector valued. You can have many values, so it can have many outputs. And instead of just a single neuron, we hook one neuron up to the next. And they each have weights. We weight the input, and we weight the output of the contributions of the individual neurons in terms of how they feed the next neuron. And the whole problem amounts to training this sophisticated network. Okay, so coming up with the appropriate weights. Okay, I'm not going to go over this too much. Okay, this is what we call a feed-forward neural network. Not all networks that we study are feed-forward neural networks, but these are the most common. And as I said, the key to working with these networks is training the weights so that they can effectively predict new values given the values of old input. Okay, so without going into great detail of this, let me describe just two types of advanced networks that are in great use in contemporary practice. So the first type is convolutional neural networks. Okay, this type of network is modeled after our understanding of the visual cortex, and it's typically applied to visual problems. So specifically recognizing dogs in images or other objects in